Hello friends, I am Amir Anwar Nizami and today we are going to study the concepts of response spectra and its Matlab code. So first we will study the concepts that what is a response spectra and then how to code it, then we will know on Matlab. So first of all, let's start with a single degree of freedom system. So at time duration t equals to 0 second, there is no displacement, and at t equals to 2 second it is a time duration. When the load is applied at 2 seconds, the deformation is 1 mm, and at t equals to 3 second you can say the deformation is 3 mm, that is positive 3 mm, and then at t equals to 4 second it is 1.8 mm, and at t equals to 5 second it is minus of 2.5 mm. Means in the dynamic load we know that the direction changes. So with respect to time, it's load is a function of time, and directions also changes with time. So here it is the 1 mm displacement deformation at 2 second, and at t equals to 3 second duration the deformation is 3 mm, then 1.8 mm and minus 2.5 mm. So what we are interested as a structural engineer, we want the maximum displacement. So at t equals to 3 second we are seeing that there is the maximum displacement. So it is the interest, it is our interest that we want the maximum displacement or peak displacement or peak deformation or peak response. So as an structural engineer we will pick up this value, and this value we are not interested in this, because if any structure is safe, because it is a peak displacement 3 mm, then it would save in all of these. So therefore at t equals to 3 seconds we can say we are interested that our deformation is 3 mm, that is the maximum deformation. Now, there is some terminology which is used here: single degree of freedom system, damping ratio, time period, circular natural frequency, time duration or time history, and the displacement response versus time duration. So we will see all these things one by one. So let's start with the single degree of freedom system. That we assume that there is a spring and a dashpot system with a mass. So we say mass dashpot system. This is the coefficient of friction with the velocity. It gives the damping force, and this with the displacement it gives the spring force or restoring force. And this is the mass. When an applied force is there or any deformation or any initial velocity is given, then it will just accelerate. So inertial force would develop here, so that we will tell mu double dot. So therefore the formula would be mu double dot plus u dot plus k of u equals to p of t when any external load is applied here. And this for the structural system, this we assume that a building is of this frame where the mass is concentrated at the slab level and the column is massless, and the stiffness is there in the mass in the column. We are interested in the stiffness of the column, so it provides the stiffness here, and it is the combination to just replicate these things that are coefficient of friction is there, which is just for the damping case. So we generalize it with a simple diagram, that is we say it also has a equivalent single degree of freedom system. So these all represent a single degree of freedom system. Now the damping ratio. So we know that damping ratio xi is C by CCR, where C is the coefficient of damping and CCR is the critical damping coefficient. So its value is 2m omega n, and we should know that xi, when xi is 0 and 1, the value of xi is 0 and 1, then it is under damped, and when xi equals to 1, then it is critically damped, and when xi is greater than 1, it is over damped, and xi equals to 0, then it is undamped. So when xi is under damped, most of the structure are under damped, so there would be the vibration or oscillation in the building. When so oscillation will die with time, okay, duration. And critically damped, oscillation will get ceased, oscillation gets ceased, means it gets stopped. And overdamped, it is more that it do not complete the oscillation, single oscillation, so it's overdamped if xi equals to 2 or something. So most of the applications are there in the door. We know that when we open the door, that is overdamped, then it comes back with a very slow movement. So that is the example of door, that where we use the overdamped case. And undamped, so in ideal case there is nothing like undamped case, because everything is there with having some dampness. So xi equals to 0, then oscillation will always occur, so it would not dies with time. And now we will see the time period. So time period of circular natural frequency, so it is the time taken by a structure to complete one complete oscillation, is called time period. It is called a time period, and we generally denote it with capital T, that is the time period. So time period is also having a relation with the natural circular natural frequency, that is called omega n, and that is relation is 2 pi by omega n. So omega n, that is the natural frequency, is under root times k by m, where k is the stiffness of the structure or single degree of freedom system, and m is the mass of the single degree of freedom system. So basically, if there is any single degree of freedom system and we want to find, so it would having some height, so the stiffness is related with the height. So somewhere it is ei by l cube, ei by h cube, 12 ei by h cube, 12 ei by h cube, or 3 I by h cube, or something with the cubic or some values with that stiffness. So stiffness is related inversely with the height. So we can say that stiffness is inversely related with height or length. So therefore it is directly related with the time period. So more longer the structure, more would be the time period. So here we have designated that structure A, B and C, three structures we have considered. So its height is h1, its height is h2, and this height is h3. So h3 is largest, so therefore we can say that T3 would be having the largest period. So it will take the largest time to complete one oscillation. Means it will go to this, then it will come back and go this, then it will come back. So it will take maximum time, because as the height would be larger, it will move larger deflection, so it would take more time to just oscillate. So it will take less time than that, and it would take the least time in comparative to other tools. So we can say that the longer the structure, that would take the larger time period. So generally, higher or taller the buildings, the time period is larger to that. So what we do here, that for a single degree, for converting a single degree of freedom system, any structure, we generally have a multi degree of freedom system, but we are only focusing here at the single degree of freedom system. So we convert all the structures if its time period is 2 seconds, suppose. So we will assume that it is a single degree of freedom system and whose time period is 2 seconds. So any structure, we will just replicate it with a 1 degree of freedom system, single degree of freedom system, and then we'll solve the problem. That whole mass and lumping, all these. Now there is one more term, it is the time duration. So there is the difference between time period and time duration. Time duration, we are just symbol is small t, we are replicating. So the duration up to which the load is applied or the response is recorded. So here we can see this is the ground acceleration, that is a ground acceleration or earthquake acceleration. That earthquake is acting at the base of a building, so the building will vibrate or oscillate. So the oscillation is recorded here. So we know that it would having a response, that displacement, velocity or acceleration response. So here the displacement record is displacement is recorded here. Okay, so this is the force, applied force. So we can say here that it is the applied force, applied ground acceleration, acceleration, earthquake force, earthquake forces, and here it will give the response or displacement response, we can say displacement response of building, of building. Okay, so we are getting the displacement response of a building. So this building is right now for us is a simple single degree of freedom, because we have assumed it as a single degree of freedom system, and we are behaving it, that whole mass is just assumed at the top. Okay, and this top would oscillate left and right and left. Okay, so here it will oscillate. So it the oscillation would be there with the time duration. Okay, for 80 seconds or any time, if you have recorded for the 80-second ground acceleration is there, and the response. So it would be a function, the this deformation would be a function of time. Okay, so at time, some time, here we can see the peak would be, I think here is minus of 40, it's crossing this value. So this would be the maximum response at this time. Okay, so somewhere it would have in the negative. So I think here in the negative direction at this position, it would have maximum response, maximum displacement response or deformation response here. So the force is applied at the base, means earthquake acceleration. It will oscillate, the building oscillate, and the response is recorded here. So at each and every duration of the earthquake acceleration or earthquake ground acceleration, the response is recorded here, and the peak response, when maximum deformation is occurring on the left of that, so it is recorded here on the negative side. We are considering this as positive and this negative, so this is negative side, the maximum recorded deformation is there. Okay, so we as an structural engineer are interested in the maximum response, that we will record this value, that we will take pick up this value, and we will save somewhere that the maximum response is, suppose here is minus 40.5 mm, suppose. So we are only concerned with the magnitude, that we believe that 40.5 mm is the maximum deformation occurring here. Okay, so this is the time duration here, this is the time duration which we are talking here mainly now. So displacement response versus time duration. So here it is the displacement response. So the displacement response here, it is for the time 2.5 second. Here it is for the 1 second, it is for 1.5 second, and it is for 2 seconds. So it is the time period of the structure, that we can say that a structure is there whose, we can say, a very tall, sorry, let me just take a white color. That this building is having a time period of 2.5 second. Similarly, this building will have time period of 1 second. This building would have a time period of 2 seconds. And it is 1.5 seconds. This building will have a height of 1.5 seconds. So when that ground acceleration is acting on this, means the earthquake force was acting on all of these, the same earthquake force is acting, then it would have this response. For the time period of 2.5 seconds, this would be the response. For 1 second time period, this would be the response. For a time period of 1.5 seconds, and for time period of 2 seconds, this would be the response. Also, because it is a damped vibration, so we have considered a constant xi here. So we have recorded all these values at xi equals to 0.02, means 2% damping. 0.02, 0.02 xi equals to 0.02. So we will see the peak here, that the peak response is somewhere close to here. The peak is here. For this 2.5 seconds time period, we are having a maximum deformation at this position. Similarly, for one time period of 1 seconds, we will just see that where we are getting. So we are getting the maximum deformation at this point. Similarly, for displacement response, we will get some deformation at peak is here, and here for this value we will see the peak response for 1.5 second is this. So we will plot the value, that here these values displacement response are given with the duration, time duration, that uh, for 80 seconds or for 60 seconds the time duration is given, and this is the displacement response for a building having a time period or oscillation 2.5 seconds, and xi value, damping coefficient, damping ratio is 2%. So each structure is having a damping ratio of 2%, and a time period is varying here for all the structures, and we have recorded the response. So for different time period, this is t here, and here we will say that we are having the displacement, or we can say peak displacement, or maximum displacement, and these all are recorded at xi equals to 2%, or we can say 0.02. Okay, so we will just catch up all the values, that at t equals to 1 second we are having some values near 35, then somewhere at t equals to 2 seconds or 1.5 seconds we are having a value of minus 40. So minus 30, minus 40. Okay, then At 2 seconds we are having a values of somewhere as -20, and then we are having at 2.5 seconds as some value near -10, -12. So some curve would be like this. Hence we have taken the t as 0.5 seconds, dt as 0.5 seconds. We have to take a small size so that it would be much better approximation. So it is the peak response or maximum displacement response with the time period. It is with the time period that we have taken four different time periods with a constant damping ratio. So we have taken the time period here on this axis, and on the y-axis we have considered the maximum response that all we have recorded. So this what we have observed here is the response spectra. It is called the response spectra. So we have plotted the response spectra. So we can say that response spectra, we can now define that it is the response, it is the maximum or peak displacement with time period at a constant damping ratio. So it is a plot of a peak response with respect to time period for a constant damping ratio. So for a constant damping ratio, all is xi equals to 2%, and time period is varying. So we have taken the time period on the x-axis, and the maximum peak displacements of all the four cases here. So we are taking the peak displacements for the same ground acceleration. Earthquake force or ground acceleration is same for all the four types of building. This same earthquake is acting on this building, and all four cases. Okay, so the plot, the maximum plot, what we can say that it is the plot of peak displacement or peak response, we can say in general, whether displacement, velocity, or acceleration. So peak displacement or response, peak response with respect to time period at constant damping ratio. Damping ratio. Xi is constant for all the cases. So this is called the response spectra. So we can see here that we have applied on a building, that this building was with a 1 second time period. So let's just, we have just shown this just once again. We just t equals to 1 second for this building. For this building it is 1.5 seconds, somewhere some more longer, 1.5 second time period of this building. This building would have more than that. It would have t equals to 2 seconds, and this building would have maximum, that is t equals to, we can say 3 seconds or 2.5 seconds. Okay, so the same earthquake acceleration is acting at the base of all, to this, to this, to this, and to this structure. All the four different structures having the time period of 1 second, 1.5 seconds, 2 seconds, and 2.5 seconds. This earthquake acceleration is acting, ground acceleration is acting, and corresponding to this 1 second, this is the response. For 1.5 second, this is the response. 2 second, this is the response, and 2.5 second, this is the response. Okay, so for each individual structure, and all the structures having the same thing is common, is that all is having a 2% damping. Suppose we are having a 2%, it may be 5%, any constant damping. So we are just considering a numerical value as 2% damping, is equals to 2% damping. So for a constant damping ratio, the peak deformation is recorded from all the parts, from this and from this. So when we will go to that for 1 seconds, we will just go to the peak value, for 2, 3 and so on. So we will just have record the all the peak values, and it would be the finally it would give the response spectrum. So we got the response spectra. So now we will just go to the MATLAB and see how to make a code, or how to plot it using a MATLAB coding. So let's see. First, we will just record the earthquake data. So we will have the ground acceleration, and that name is IS1893 code. We have just given the name to that, and the command is text read. So it will record that earthquake E. Okay. And the time history, we are just discretizing that time history up to 80 seconds, and that will start from 0 to 80, and at a time interval of dt delta t, we can say that is 0.02. And with the time history, that is small t, we are just showing that time history. Xi value, that is the damping ratio here, and damping ratio we are just making a constant value as 0.02. And t is the capital T is the time period. So we have taken the structures from 0 to 3 seconds of the building. So it is also discretized with 0.01. And now the mass is 1, and the natural frequency we know that is 2 pi by t. So if t is a vector, because it would be 0, 0.01, 0.02. So a lot of structures having different time period of the building, it will take all those. So it would be a complete column format. So therefore omega n would also be a column vector, and k is m times omega n square. So if this value t is changing, therefore omega n will also have a column vector, then stiffness k would also be a column vector. Okay. So now first of all, we will see that in the last lecture we have solved for the response of a building, that how we find the response, and how we have the MATLAB code for that. So here the input data we are all having xi, we are having time period of the building, mass we are having. So and omega n we get from there, and stiffness also we get from the formula. Now we are having these inputs, so we would form a function first, that is the formulation. We have given that function name. So we'll see what is this. So here it is, we want the output of displacement and velocity, and the function name is formulation, and the input is xi, m, k, earthquake values, that is the ground acceleration, dt, and omega n and small t. So that is the omega d, which we are knowing, that is the damped frequency, which is omega n square root of 1 minus xi square. Similarly, this shortcut or shorthand of sqrt we have written as sq equals to this ep, that is exponential of minus I omega n dt. Similarly psi, and all these values we have written a, b, c, d. In the last lectures we have seen all these value, a prime, b prime, c prime, d prime, we have taken these values, and then we have just formed a u and v column matrices here. And then the initial conditions were given as u0 equals to 0 and v0 equals to 0. And we have just we know that u naught and v naught in the column vectors, it starts from, if we are having any column, then it starts from first position 1 to n. So therefore it will start from u of 1, that would be u naught, and v of 1 will save at first position of v naught. Now we know that when we were interested in finding the displacement response for a structure, then we used to have a loop that u of I plus 1 was a of ui b vi c into this and d into this value. Similarly, the velocity u dot I plus 1 would be this value, where a b c d all other constant coefficients we know those values, ui vi ei and ei plus 1 we are knowing all these values. Here ei and ei plus 1 is the acceleration, ground acceleration, so we are knowing these values, so we can find the ui plus 1 and vi plus 1. It becomes a recurrence formula, so therefore a loop will act again and again. When ui plus 1 I would be 1, then it would be 2 u2 and v2. Then again when I would be 2, then it will become u3 v3, then this side would become u2 v2. So one again and again it would just have a recurrence relation, and finally it will end out, and then we will come and we will see here that for j equals to 1 to length of t is the time period, and we have a column vector, we know that we have discretized with the point 0 1 dt. So therefore it would also have a column vector of length, size of that is length of t. So omega n, that would be the frequency, would be omega n under or with j, that is the loop we have applied, and the small stiffness value would be capital K of j, and the output would be here because we have made the function, so we will call that function uv equals to formulation of this. And the maximum displacement, because we have a command that we want to find the maximum displacement, we have seen from all we were interested in the maximum displacement, so we write the command as maximum of absolute value of u, because we want that only magnitude, we are not interested in the sign whether it's positive or negative. So that's why we are writing a command, matlab command, that max of absolute of u, so this would give the maximum deformation or displacement here. So this maximum displacement is nothing but it is a plot with the maximum displacement versus time period. With respect to time period we are plotting. So therefore, and a constant xi was constant, that was 0.02, means 2% damping. So it would give the maximum response spectra or displacement response spectra. Therefore, we also know that pseudo spectral velocity would be nothing but omega n times the spectral displacement, and pseudo spectral acceleration would be equals to spectral displacement with multiplied by omega n square. This we can remove because this was nothing but a conversion unit. When the value is given in the g unit, then we can multiply it with 386.09 to make it in the inch per square unit. So that's the unit conversion value, so we are not interested in those things right now. And now we will plot the with on the x-axis as time period, and then the maximum displacement or spectral displacement. Similarly, we will plot time period with the x-axis would be the time period and the pseudo-spectral velocity and pseudo-spectral acceleration. So we will see, let's plot. So here this is the spectral acceleration plot, we can see here with different time period. Here it is the time period, not the time duration. Note that it is not the time duration but it is the time period. This plot is with the time period, okay. And here it is the spectral velocity versus time period, it is the plot. It is also for a constant xi, that is 2% damping, and here it is the spectral displacement with respect to time period for a constant damping, that is xi equals to 2%. So we have seen the MATLAB coding and the results for each. It is the acceleration, it is the velocity, and this is the spectral displacement. So what is the benefit or why we are interested in finding these? Suppose let us discuss with displacement first. So if we are having any building then we are interested in designing the building that for the maximum deformation. Okay, so let me just go to our slide. So let us see here. Yeah, yes. So here if we are having any value, if our structure lies somewhere here, that we are given the plot area and the column size and all, so we can get the, for that building we can get the time period of that building we can find. So if the time period lies between here somewhere 1.25 seconds suppose, so it is lying here. So we are not having the time history data or any earthquake data for that place. So for those, that place we will just go to this value somewhere, and we will see the peak value for this. Then for corresponding to that, we'll see that maximum displacement is how much. So this would give the maximum displacement. So corresponding to this displacement we will design that building. Hence this is response spectra. But for design purposes, what we do, we take a lot of response spectra from different earthquakes, ground acceleration, superposing on the same structure, and then we make a very smooth curve from there. So that is called a design spectrum, which we are interested, so that the smoothness would be there. Okay, so we have seen the response spectra and how it plots on the MATLAB. So thank you.